Okay. All right. So, good evening, everyone, and welcome to the first session of our online workshop series, Tracing Climate Change. This idea actually started a few years ago during one of my field missions in Idre in Sweden. It was there that I realized how important it is to discuss the impacts of climate change across different geomorphic environments. I feel very grateful that my fellow geomorphologists like the idea, support the idea, and together we have made it a reality. It is a great pleasure to host you here, bringing together students, researchers, and professionals from across Europe to explore the geomorphological impacts of climate change. Over the coming weeks, we will dive into dynamic landscapes from coastal and deltaic systems that we will discuss today to mountain regions and see how climate change is shaping them. This series is not just about sharing knowledge, it is about creating connections, asking questions, and inspiring actions in our perspective fields. This is why I have asked today Alasdair to be here, but I will explain later why. So I encourage everyone to again participate actively and enjoy the discussions. Thank you for joining us, and I hope you find this workshop fruitful, inspiring, and thought-provoking. And before we start, I would like to give the floor to Michaela Verga. Dr. Michaela Verga is a senior lecturer at the Faculty of Geography at the University of Bucharest. Michaela specializes in environmental sciences, applied geography, environmental geomorphology, natural hazards and risks. Her applied research has been focused on landscape dynamics in the Carpathian region mainly, slope movements, landslides impact on road infrastructure, vulnerability analysis of different cultural heritage sites, and many more. She's the leader of the TRACE project, and I would like to thank her from the bottom of my heart for accepting to take this role and to coordinate this effort the last all of these years. So, Michaela, the floor is yours.
Thank you very much, Nikki, for this warmful introduction. I'm very glad to be here at this moment when our project becomes a reality and reach its direct beneficiary, you, our students. As Professor Evelpidou says, this project idea came from a previous field trip during one of our past collaboration, showing how valuable ideas can emerge when people with shared interest come together. That's why your presence today isn't just about professional growth, but also about building social skills and networking. From this point of view, it might be helpful to share the contact list of all the participants at the end of workshop series, if all of you do agree with that. What is tracing climate change, shortly called TRACE? I will share my screen in order to follow some ideas and to highlight a few information. Just confirm me if you see my screen.
Yes, we can.
I'm not here. Just a moment. Beginning. Okay, now. Good. PRAISE project, it's an Erasmus Plus project, founded initiative supported by European Union, designed to promote higher education collaboration and to provide geomorphological knowledge while training young people in professional, social, and digital skills. The project brought together partners specializing in different geomorphological fields to offer students a diverse range of knowledge, skills, and experience. There are three universities partner involved in this project. University of Bucharest as coordinating partners, National and Capodistrian University of Athens, and Aix-Marseille University, all three responsible for the scientific content of this project. And also, we have as a partner an educational association named E3STEM, engaged in developing open STEAM applications based on transdisciplinary and interdisciplinary approach. The project aim to offer students the opportunity to get to know new landscapes, to understand how similar formation have been developed in different geomorphological environments, as well as to examine the imprints of climate change and tectonic movements, those renewing the knowledge in the courses related to geomorphology by applying modern techniques and methodology. The main objective of our project are as follows: to study geomorphological evidence of climate change, to understand how landscape evolved due to this climate change, to use modern geoscience techniques and methods to help students understand and explore unfamiliar environments, and to compare similar landforms in different geomorphological settings. Through all its activities, the project was designed to provide students from various countries and with different academic backgrounds a comprehensive understanding of how climate change affect various geomorphological environments. Additionally, it seeks to develop students' advanced analytical skills in applying STEM, science, technology, engineering, and mathematics methods to analyze and interpret changes in the terrestrial landscapes with a focus on physical features. This approach will not only enhance your understanding of climate change, but also will contribute to prepare you to contribute to discussions and solutions regarding environmental sustainability and landscape management. The project included research studies on the following topics: paleogeography, which helps students understand how landscapes in various geomorphological settings were reconstructed and influenced by human activities that also were affected by climate change. Additionally, reconstructing and mapping ancient shorelines enhanced the understanding of these processes. Another topic is morphotectonics, which refers to the methods used to assess how tectonic forces shapes the Earth's surfaces, as the morphology and structure of recent sediments are heavily influenced by tectonic activity, particularly neotectonics. Another topic is climate change, such as interglacial and glacier period and the disruption in their cycles due to anthropic interventions, as well as their effect on coastal and deltaic environments. Last but not least, essential climate variables such as permafrost and sea level indicators contributing to the study of global changes and their environmental impact. The planned activities within projects aimed to achieve the main goal of providing students with relevant information and also to engage them in understanding the scientific content. So the first half of the project timeline was dedicated to field work, primarily focused on coastal and deltaic regions. The data and information collected were used to create educational resources, and now we are at this point of delivering the scientific content to you through these weekly meetings as workshops. Field trips were carried out in 3 case studies in Romania to study delta progradation and its relationship with sea level changes, and also to understand shoreline dynamics. But another idea was to analyze low altitude permafrost as a key indicator of global climate change. Another study site was Greece and also in France to understand sea level changes due to neotectonic movements and climate change. On this map are pointed out all sites of interest. Some of this fieldwork benefit from student involvement via joint educational programs like CIVIS BIPs or through individual interest. Fieldwork involved mapping, measurements, topographical and geophysical survey using drones or other specific instruments, geospatial data gather, and rock samples collection through coring. The collected samples were then subject to laboratory analysis to reconstruct past geomorphological events. All these activities result in an impressive collection of data and information completed with very strong documentation from bibliographic references. You may see in these images a small part of our activities and experience during field trips, and you may recognize the faces of some of your colleagues as well. But why did we conduct all this field research? As I told you, to gather current and validated information on the dynamics of various geomorphological environments and how climate influenced their development. This information served as the foundation for creating different educational materials, such as lecture notes, presentations, interactive maps, virtual field trips, video lessons, and some exercises in order to assess how this information were gathered with topics like understanding climate change, coastal landscape and coastline dynamics, deltas in Anthropocene, mountain system and mountain permafrost, understanding vulnerability of coastal environment. These resources are available for free and using an open access platform. The only thing that you need is to create a personal account in order to use them. To find this platform, you should Google the project website, Trace Project UB. UB came from University of Bucharest, which is the coordinating institution. On the left corner of the web page, you will find this button, Open eClass. The only obstacle you might encounter is that the dialog window first appears in Greek when you access the platform. But if you will use the second button from the left on the upper corner, you can change the language and everything will become much easier. And you will access the page of our project using the main menu of this page. You may find educational material on different sections, such as documents and multimedia. The final phase of the project is the implementation through the series of online workshops dedicated to students from the 3 partner universities in order to promote climate change and its effect on geomorphological environments. The series of online workshops will consist of one workshop per week for 1 month for each participating university. That means that during this month, March, National and Capodistrian University of Athens organize workshops for their students, but not only, as you already see, there are participants from other universities. During April, University of Bucharest will organize workshops for their students, and during May, Aix-Marseille University will also host workshops for their students. The program of these workshops is as follows, with 4 different subjects, but very much related one to another. So this series of workshops will cover topics such as formation, evolution, and progress of various landforms in coastal and deltaic environments in each respective country, as well as the effect of climate change on these environments. The workshops will emphasize the importance of paleo shorelines, coastal morphology, tectonic movements and their involvement in coastal dynamic, and the impact of climate change on this environment in general. But this will not be the end of our activity. We want to let people know about our research studies and our scientific content, and also about your involvement. So we are going to collect successful stories from these online workshops. This will include photos, testimonials, lessons learned, examples. Our colleagues from E3 STEMs will gather and edit all this information and include them in a booklet, which will be also available for download through the project website. Therefore, I will kindly ask you, if you will be contacted by our colleagues from E3 STEM, please cooperate and provide them with the necessary information so that this booklet to be truly successful. Last but not least, it is very important to keep you updated with all the information regarding project content. So please follow us on using the project website. You may see it here, but also becoming friends and followers on our social media pages. You have here all the pages available to be consulted. This being said, I will thank you very much for your participation in these online workshops. And I also hope to see you in the future in our common educational programs, because we are very much involved in such events. Thank you. And now I will pass the mics to Nikki.
Thank you very much, Mihaela. Can you please stop sharing? Yes, great. Okay, thank you very much. Now, I'm very glad to see that we have so many participants. I mean, it is more than 100 right now, and I see 90 of them are students of our university. We have some students from abroad, but 90 of them are from National and Kapodistrian University of Athens, so you still have more students, Michael, for your workshop next month. Okay, so it's time to introduce you Professor Alasdair Skelton. He's a professor of geochemistry and petrology at Stockholm University. His published works are on petrology, climate the climate of the past and the ongoing climate crisis. He was a co-director of the Bolin Center for Climate Research for 9 years. Presently, he is a chairperson of the Education Board at Stockholm University and chairperson of the European Civic University, and specifically the Hub on Climate, Environment and Energy. He is strongly committed and actively involved in educating about geology and climate at all levels, from preschool to research training, both within and beyond academia. He is co-founder of the Researchers Desk, which is a civil society organization against climate actions, which serves as a meeting place for academia and activism. And in fact, he's an activist himself. Now, beyond the usual formalities, I want to say a few words about what Alasdair means to me personally and professionally. Most of you already know me. I don't really do that, but I think that here we have an exception. Alasdair, it is an inspiration to me, both as a person and as a scientist. Over my career, I have met many scientists, but Alasdair stands out. Above all, he is a true human being, a quality whose deep meaning is often forgotten in today's world. It is a great honor for me to have met him, and I feel profound gratitude for having collaborated with him. He has inspired me as a teacher, and I invited him today with us with the conviction that he will inspire you as well. The next generation of scientists, the next generation of researchers who will carry the torch. So I sincerely thank him for accepting my invitation, giving my students the opportunity to meet and learn from him. Alasdair, thank you so much. The floor is yours.
Thank you so much, Nikki. That was probably the most lovely introduction I've ever been given. I really thank you so much for that. I'm just going to check. Are you hearing me well enough? Sound okay?
Yes.
And I'm also going to share I'm going to share slides with you, and I'm just going to make sure that that actually works. Have I successfully shared slides with you?
Yes.
That's just amazing. That's good. Excellent. What an amazing initiative I've just managed to crash into. It sounds like you've been doing wonderful things. It's really a privilege for me to join you for a brief visit. Nikki contacted me and was super happy to be able to be with you. I'm going to give you a brief talk about taking on the climate crisis. As Nikki rightly said, I'm both a climate researcher and also a climate activist. I'm a climate activist because I need to be. I think that this talk will hopefully be understandable. I'm going to, and if you find it's too basic, please accept my apologies. Instead, think of it as a way of helping you explain concepts to other people if you find it all a bit basic. So I'm going to talk you through, this is a short, we can maybe think of this as a crash course in taking on the climate crisis, which you're already doing by doing research on geomorphology and past climate. You're already a part of the solution, but more of that a little bit later. I'm going to frame this short course with 5 sentences. And this is a summary of 6 generations of IPCC reports, summarized in just 12 words. It's warming, it's us, we're sure, it's bad, and we can fix it. A simple enough message, it fits on a t-shirt. But behind those 5 sentences is a huge amount of science. And let's just walk through those 5 points. Let's begin by it's warming. Now, how do we really know? It's actually a bit harder than one might think. I'm sitting in Stockholm, Sweden, talking to you at the moment. Outside, it's about 8 degrees. Last weekend, it was -2. The temperature goes up and down. How do we work out that it's warming? Now, I understand that most of my audience today is from Greece. So for those of you not from Greece, please forgive that all the examples are from Greece. The way we realize it's warming, the way we can actually see it, is by looking at temperature over a long time. And what I'm going to show you here is how temperature has varied in Greece since 1850. I'm not going to show one of those classic nerdy scientific curves. Instead, I'm going to use a technique known as warming stripes, which were devised by Ed Hawkins and are a beautiful visualization of temperatures that are easier to convey. So when you're out conveying this type of material to the public, I recommend using warming stripes, because one of the things I want you to think of as you've come into, you're now working on geomorphology research, is you are spokespeople for the climate. You're spokespeople for the geological time. So take these tools and use them. Okay, so what I'm going to do is I'm going to show white from 1850 up until the present. I'm going to use white stripes for normal years in Greece. Now, normal in Greece, based on an average between 1960 and 2010, is 18 degrees. That's an average for the whole year. Obviously, it's hotter in the summer and cooler in the winter. Warmer years would be up in the 20s, and cooler years are down about 17, 16 degrees. So if I animate that figure, what we see is there's variation, of course, year-to-year variation. That year-to-year variation is due to natural factors such as volcanic eruptions. They transiently cool the climate, and also changes in ocean circulation. But what you also see is the past 2 decades are all warm, all warmer than normal. That's climate change. By measuring temperature over a long period of time, we can see that it's warming. But just noting that it's warming does not tell us that it's us. The next step is to work out, how do you make sure it's us? Let me show the same data, but I'm not going to show it for Greece now. I'm going to show it for the entire world. And because the entire world doesn't have the same temperature everywhere, we're going to look at change of temperature. So we look at warming compared to normal. And here we're going to define normal the same way as the IPCC does it, between 1850 and 1900, which is the earliest time we've got a lot of measurement data. And when we look at this curve, we see that it's warming. We see that temperatures risen by about 1.3 degrees compared to normal. And that most of that rise has happened towards the end of the 1900s into the 2000s. But that in itself does not tell us that it's us. So how do we work out that it's us? Well, what we can do is we can generate climate models, which is just basically putting all of the climate, all the things we know about the climate into a computer, and doing and modeling what the climate would be. And we can basically regenerate this curve. But what we can also do is we can take away factors. So let's just take away one. Let's take away us. And let's use lots of climate models and see what the temperature would have done. And that's what natural processes would have led to. We still see variation. That's due to ocean circulation changes and volcanic eruptions, but that big rise is not there. So that's a big finger pointing at us, saying that it's us. And we can kind of fill that gap, that rise in temperature, with our emissions, which when we superimpose them, we see that our emissions basically correlate with that rise in temperature. Now, that per se, so we see now our emissions, we see the temperature is rising. Coincidence and timing is not proof of cause and effect. To prove cause and effect, we have to have a mechanism linking our emissions to the temperature rise. Well, there is one, and we're absolutely sure about that. And that comes to the third part of this short course. So we're sure. And what we're sure about is that there are 3 factors that control Earth's climate. They are sunlight. Those of you who want to be sophisticated might prefer phrases like solar insolation, but sunlight will do. The albedo effect and the greenhouse effect. Now, those are concepts that you not only need to understand, you need to be able to explain them for everybody. You need to be able to explain them as much, they're as important as understanding how to read and write and how to do simple arithmetic, understanding these 3 factors. But they're really straightforward. They're so simple, my cat can explain them for you. So meet my cat. This cat is called Charlotte, which is completely irrelevant. You don't really need to know what she's called. She's really sweet. She might actually come in while I'm talking, for all we know. But that's not what's really important about it. She's a cat. What's important is cats like to be warm. So what does the cat do? It sits in the sun. It sits in a sunbeam. And what's it doing when it's in the sunbeam? It's receiving energy from the sun. And how's that energy reaching the cat? It's coming in the form of sunlight. Now that energy changes the temperature of the cat. It also changes the temperature of the Earth, from the temperature of outer space, which is really rather cold, to +6 degrees. Now, that cat has its temperature's increased because it's absorbed that energy in the form of sunlight. And then it converts that sunlight into heat. It doesn't convert it into light. And you can, and the cat then radiates heat. So does the Earth. You know that a cat radiates heat because if you pat it, it feels warm. And you can really, and it's a simple experiment you can do at home, is take a cat out of the sunbeam. It'll already not be very happy, but do so anyhow. Go into a cupboard, a dark cupboard, close the door with yourself on the inside and the cat, and look at the cat. You can't see it. It's not glowing in the dark. It's not radiating light. Pat it. It's warm. It is radiating heat. That cat's converted sunlight to heat, which is exactly what the Earth does. Now, if the Earth was entirely black, its temperature would be 6 degrees, but it's not entirely black. It's kind of a bit more like the cat. It's a bit more multicolored. And because it's got different colors, we have to also consider the albedo effect. Now, those of you who are observant will notice this is not the same cat. This is Charlotte's sister. Her name is Ellen. She's not as nice as Charlotte, and my daughter has stolen her and taken her to another town. But she has got one thing in common with Charlotte, and that's because she's got white fur. And that white fur reflects sunlight. So that means some of the sunlight that hits the cat never changes the temperature of the cat, never warms it up. And the same thing happens to the Earth, because the Earth is not black at all. It's multicolored. And the brighter parts of the Earth reflect sunlight. And that actually cools the Earth. That's the albedo effect. Pulling the temperature down would be minus 18 degrees if Earth didn't have an atmosphere. But Earth does. Now, so that means we need to introduce a third factor, and that's the greenhouse effect. Now, those of you who are really good with cats will now already know that this is the second cat. That's Ellen. You can tell it's got a brown nose. Now, that cat has it's absorbed lots of sunlight, energy, and it's warm and happy, and it wants to stay that way. So how does it solve it? It creeps underneath a blanket, which means the energy it's radiating out in the form of heat is trapped by the blanket and sent back to the cat. That keeps the cat warm, and the cat's happy. That's why cats underneath blankets purr. Now, that's basically the same way as the greenhouse effect works on Earth. And the greenhouse effect raises Earth's temperature, would raise it naturally to 14 degrees. But there's a key difference between the greenhouse effect and this blanket. This blanket would not allow sunlight to pass through because it's black. So let's change the blanket. Let's make it transparent. There, now you can see the cat's ears. That blanket now allows sunlight to pass in, but it traps heat when it goes out. And that's the way the greenhouse effect works. And the strength of the greenhouse effect is controlled by the amount of greenhouse gases in the air. And the one we need to think about most is carbon dioxide, because it's long-lived. It stays, when you raise its concentration, it stays high for a very long time. So we need to know where carbon dioxide comes from. And that's something that you as geoscientists are the spokesman people for. Carbon dioxide, you all know where it comes from. Carbon dioxide comes from volcanoes. That's the natural source of carbon dioxide. When they erupt, it's not just lava and ash, it's also carbon dioxide. And what's really cool is all the volcanoes since the formation of the Earth have been adding carbon dioxide to the atmosphere, but they've never changed the amount in the atmosphere. It stayed the same. So how could that possibly be the case? How could all those volcanic eruptions never raise the carbon dioxide concentration in the atmosphere? Simply because it's part of a cycle. There's a similar process that takes the carbon dioxide away. So the same amount of carbon dioxide is removed from the air by the weathering of rocks. What does that mean? Well, you guys know, as geomorphologists, the rocks are dissolving. There's a bunch of chemistry going on, which I'm not going to go into. I don't have time for that. You want to nerd down later, I'll talk about the reactions. But what we see is that, and that's actually kind of really elegantly set up. The rocks dissolve the weather just at the right rate to maintain a stable climate. And that stable climate has been the basis of life on this planet for 3.5 billion years. And we know that because we found fossils that are 3.5 billion years old. So that's nature. So what's the problem? Well, it's really straightforward. We're emitting carbon dioxide faster than it can be removed by the weathering of rocks. So there's a backlog. There's carbon dioxide left in the atmosphere. And that's what causes global warming. And that's the problem. It's that straightforward. The natural sink for carbon dioxide is weathering of rocks, and we're emitting it too fast. Now, you're probably thinking, doesn't this guy know anything about trees? And yes, he does. Trees take carbon dioxide out of the atmosphere, out when they photosynthesize, and then they die and put it back in again. It's a loop. We're emitting geological carbon from rocks, so we need rocks to take it away. Okay, this causes global warming, and it's bad. That's the fourth part. It's really bad. This is just last year in Greece. The particular spate of wildfires that struck Greece in 2025 were 10 times more likely due to climate change. This is something that we forget about in the north, that Greece and Mediterranean countries are in the front line facing the climate crisis. Now, I want us to perceive the climate crisis in a different way. This is really important. These impacts are really severe, but there's a more severe impact that we sometimes don't grasp, a really severe impact. And for you to really appreciate this impact, I need to present two people for you. I need to take you to New Year's Day on 2025. And this is a photograph who shows two people who are very dear to me. The person on the left is Lily. She's my daughter. She was born in 2005. The person on the right is Karen. That's her grandmother. She was born in 1935. So you can quickly work out she was 90 in 2025. Keep that in your mind. Let me go back to the climate crisis. So what the climate crisis really means, it means more than wildfires. It means more than flooding. What it means is loss of life. When we talk about 1.5 degrees of warming, we sometimes forget what that means. What it actually means is 2% of all species of plants and animals are committed to extinction. 1.5 degrees is the goal of the Paris Agreement. Current policies are pointing at 2.7 degrees. And at 2.7 degrees of warming, 5% of all species of plants and animals are committed to extinction. That's 1 in 20. And if we fail those policies and go for business as usual, that equates to committing 30%, that's 1 in 3 of all species of plants and animals to extinction. When will that happen? When my daughter is as old as her grandmother. This is very now, very much happening. So what should I do? I'm speaking to most of my audience here are young people. Young people, like older people, will suffer from climate anxiety. What should I do if I suffer from climate anxiety? 3 things. 1, know that you're not alone. There are 20,000 climate researchers on this planet. Some of them in the room with you today. They all feel climate anxiety because they understand what's going on. Climate anxiety is simply a sign of intelligence and awareness of what's going on. The solution is to be, the cure is to be a part of the solution. And most importantly of all, know that we can fix it. Because we can. We can fix it. I live in a small country. We're only 10 million people in Sweden. Your countries are also fairly small. I very often hear, it doesn't matter what we do. I mean, the United States are 30 times the size in terms of population compared to Sweden. So what does it matter? Well, let me say it does matter, and let me illustrate. I have 2 illustrations I use. I'm going to use my favorite one. In this image, the girl to the right of Greta Thunberg is called Sophia. Sophia was one of my students. She read geology at Stockholm University. When Greta was going in a boat across the Atlantic to give her "How dare you" speech in America, Sophia and a group of her friends were organizing the largest climate demonstration that has ever happened. They put 4 million people on the streets. And that was impressive. But what was more impressive was the result. If you search for the expression climate crisis using Google searches, you will find that our awareness of the global awareness of the term climate crisis happened in conjunction with the strike that they put 4 million people on the street, the school strike for Klimatet. But that's not what's impressive. What's impressive, it's never gone down. It's still that high today. This was the most impressive education campaign I've ever heard of. So a handful of school children in Sweden changed the public awareness of the word climate, of the concept climate crisis. No one is too small to make a difference. So yes, you matter. Yes, what you can do makes a difference. And who should do something about it? Whose responsibility is it? Is it me? How often do I hear, don't put this on the individual? Is it my government? Well, the answer to that question is yes, it is you and your government. It's two-way. You need climate smart actions from your government, but your government can only do those if you accept them. It's a two-way solution. And once you decide that I'm part of the solution, I'm big enough to make a difference, then you just need to open the IPCC reports and you'll find the solution. And there are 3 of them: emissions reductions, nature-based solutions, and carbon dioxide removal, which take us to net zero, which is where we need to be. All 3 of those solutions are needed, and they're needed all at the same time. Let's illustrate. Emissions reductions, it's the biggest part. 3/4 of what we need to do focuses on emissions reductions. It's about transport. It's about what we eat. Don't eat this, it's a Scottish breakfast. You'll have a heart attack and die, and it's bad for the climate. It's where our energy comes from. It's about our infrastructure. So let me just illustrate just a few examples. Let's think about travel. Most of you are in Athens. Here's a little comparison for you. If you want to travel to Thessaloniki, here's a few options. You go by rail, car, air. And you look at this plot and you can see, well, actually air travel's better than going by car, and rail's better than all of that. But then I have to think back to a year ago. I went by train to Sweden, to Athens to meet Nikki. And Nikki wrote to me and said, don't take the train because it's dangerous. And she said that. I didn't really know why. But in Greece, you'll be thinking very much about this because it was 3 days ago you had the memorial for this event. Rail travel needs to be safe. It needs to be effective. It needs to be well looked after. Rail travel is a good example where the individual is necessary, but so is society. Society, for example, in Greece, needs to create safe, reliable rail travel, and then society needs to use it. Energy, well, you can see the different emissions for different types of energy. Obviously, we don't want to be using the fossil types of energy. What's going on in Greece? Well, Greece is quite strong with solar and wind, but there's heavy emphasis on oil and gas. This is where we obviously need to work. As an individual, choose your renewables wherever you can, and also push your policymakers to be making changes so that energy in Greece is not coming from oil and gas. Food, what you eat matters, there are about 100 different plots like this, but basically vegetarian food has less emissions than meat. So we need to be eating less meat and more vegetarian food. This is a good example where you don't necessarily tell everyone else what to do. You don't know about somebody else's culture or health situation. So don't be pointing the finger at other people telling them what to eat. But I can look at this middle-aged guy and think, this guy doesn't need all that much meat. He's got too big a belly, which you fortunately can't see. You can see it off the screen. Infrastructure is stuff like, wind turbines, the infrastructure for electric cars and so on. Well, this needs a bunch of critical raw materials if we're actually going to have infrastructure that's low on carbon. And critical raw materials come from rocks, as you well know. This is the site, Skouries in Greece, where there's been a lot of controversy, and the idea here is to mine copper. There's a lot of issues about mining. If we want less mines, there's only one way of doing it, and that's reducing consumption. Nature-based solutions are part of the solution, 20%. And this is about making friends again with nature. These are oak forests in Greece. Oaks are very, very nice, but forests are good, wetlands are good. looking after nature. And then there's carbon capture and storage. And because I'm talking to you guys, this is a very novel form of carbon capture and storage. These are beach rocks, which Nikki works on, and they're a potential future for carbon capture and storage, making these coastal barriers. So technical solutions, that's 5% of the solution. So I'm coming to the end now. So after listening to a climate lecture like this, how do I become part of the solution? Well, there are 4 tips. 1, think about your own emissions. If you can reduce them, do so. If you can't, don't. You can't do anything about it then. But what you can reduce. If you've got any money, now many of you students, you don't have any money, but when you've got money, make sure that what you're investing in is fossil free, that you're not actually funding the fossil fuel industry. Your voice is the most important thing often that you have. Speak out, educate, share knowledge with other people. And then think about what your special talent is. What makes you, you? What is your special gift to the world? It might be research, it might be your geomorphology research, but maybe it's something completely different. Maybe you make secondhand clothes. Maybe you're good at singing. Communicate about the climate crisis. Use whatever skills you have. There are so many things needing done. So my last slide in this type of talk is always one about hope. And I'm going to take you to a place which I love, just to talk, because I've been told you should end a climate talk with hope, and I think it's a good idea. This is one of my favorite places, and it's a place I go to when I want to think about hope. It's an oak forest on a Swedish island. It's an island called Visingsö, which is in our second biggest lake, called Vättern. And you're looking at an oak tree, but those of you who know oak trees will actually think it's a rather odd oak tree. It's tall and straight. Oak trees are not tall and straight. They're short, stocky trees. Well, this oak tree is tall and straight because it's planted with beech trees, and beech trees block out the light. So the oak tree has to grow tall to make it capture the light. This oak tree is one of many hundreds and many thousands that were planted all in the same year in 1831 by order of the Swedish Navy. And they were planted because in 1831 there was a fear there would not be oak wood for making ships in the future. When it came to harvest time in 1975, the Navy didn't want to cut down the trees to make ships, because in 1975 ships were made out of metal. So why am I showing you this? Well, imagine now that you're the person who plants the seed that's going to be this tree. Would you ever have imagined in 1831 that ships would be made in a completely new material? Probably not, because you'd be expecting the expected, which is what we do when we're thinking about the future. We expect an economy system the same as today. We expect legal systems the same as today. We expect our behavior to be the same as today. But of course it can change. Everything changes. It's not the expected that happens, it's the unexpected. So when you're thinking about the future, don't expect the expected, expect the unexpected. And now imagine yourself planting that seed that will become that oak tree one more time. You know enough about oak trees to know that you will not be alive in its harvest time. An oak tree takes over 100 years to grow, but you plant it anyhow. So why do you do that? You plant it for future generations, and that's what solving the climate crisis is about. It's about planting a seed for future generations, because every one of you who is listening to me today is too old to be here to watch when the temperature curve goes down. It takes that long. But everyone in this room is young enough to be here to watch when the emissions curves goes down. Why? Because we're going to bend that curve together. Thank you very much.
Thank you very much, Alasdair. I always enjoying watching your talks. We have more than 100 students here, and I'm very glad that they had the opportunity to listen to you. Probably, if you have some questions and you would like, you're not shy, and you would like to share your question with Alasdair, please do so. You can always come back You can always write a message if you are shy to turn on your microphone, or you can come back to him. It is easy to find him, and for sure you can also follow the researcher's desk. You can always find very interesting talks there about climate change and climate crisis. Okay, so if there is no question, probably.
I think Effie wants to
There
ask a
is.
question.
Okay, Effie, please.
Yes. Hello. I'm happy to see you again.
Hi, Effie.
And
How are you?
I'm very good, and actually I'm holding back tears again.
Well, let me cheer you up. Here's the cat.
Not very happy because last time I heard this story, it was in Uto. Oh my god. I'm sorry. And actually it was very inspiring indeed, because now I'm applying for masters. I'm finishing my degree in climate change and energy transmissions and how to manage physical disasters. Also, I was lucky to meet people that travel like you by train and use bike, and I appreciate it even more because of that. I don't really have a question, but I wanted to share this with you, and thank you very, very much.
Oh, Effie, I'm so proud of you. What you're going ahead with your career into climate and energy. That's so good. That's fantastic. You're amazing. Well done.
Well, it is a lot thanks to you.
Bless you.
And I would like to be on last year's VIP here in Greece, in Naxos, if I'm correct. But I was away in Erasmus in Italy. And there, actually, I was very lucky to meet people from Romania that now I'm doing my thesis at the Carpathians in hydrogeology and petrology, so you can understand the big impact.
That's lovely, Effie. Good luck
So,
with it.
thank you very much.
Thank you.
I never sent you the email I promised to, but I think I can still.
You can still. It'd be lovely to do. Keep in touch and tell me how you get on.
Okay,
Promise.
I promise. Thank you very much.
Thank you.
So touching, so nice. Just to let people know that last year I was organizing with Alasdair an activity in Naxos Island in Central Aegean Sea. And Alasdair arrived without using, from Stockholm, without using airplane. I don't know how to do that, but he did that.
We'll do it together at some point, Nikki.
Okay, yes. Good.
It's a nice trip. It's a bit long though.
Yeah. Good. So nice. Thank you very much once again.
Thank you for having me, and good luck with the rest of your meeting. Take care.
Thank you. Just to let you know that this series of workshops will take place in different countries. Today is in Greece. in 1 month from now, it will be in Romania, and then in 2 months from now, it will be in France. It will be a great honor if you give the same talk to the Romanian students and to the French students in order to be able to have more influence on that. If you can, if you are not available, then maybe we can always use the video, but we would like to have you there.
It would be my honor, Nikki. Please send me the dates after the meeting.
Okay, I will. Thank you so
Thank-
much, Alasdair. Thank you.
Thank you for
Nice to
having
see
me.
you, Alistair.
Nice to see you, Sophie.
Bye.
Bye. Take care. Bye-bye, Effie. Hey, Dol.
So let's go now to the next of our speakers. It is Francois Sabatier. He will discuss with us dynamic landscapes, coastal and deltaic. Francois is a professor at Aix-Marseille University. He is a coastal geomorphologist, specializing in the study of coastal processes on microtidal beaches, ranging from their long-term evolution to the impacts of storms. His research at Ceres has notably highlighted the decrease in sedimentary contributions from the Rhone to the beaches, as well as the organization of littoral drift cells along the Rhone delta, and the vulnerability of pocket beaches to rising sea levels. Currently, his work is centered on nature-based solutions, particularly focusing on the degradation or dismantling of dikes to facilitate the restoration of natural beaches. Just to let you know that Francois is part of this trace project. We had the opportunity to work together the last few years on a trace project, but he's a friend for many years. We are working together many different things, and okay, he's really a great colleague in the field. I do enjoy working together with him, and also the teaching in the field becomes something else. But today you will have it. You will have him here. So Francois, the floor is yours.
Yeah, thanks for the introduction. Well, first of all, it's always difficult to speak after an English native. So, well, I guess Greek student can understand me. And well, I'm happy to be present because, you know, it is more or less the end of this program, and it's always a pleasure to give information to discuss with the students. So I should share my screen. Okay. So as you know, we are involved in the Erasmus Plus program. Is it working for you? Yes, I think it is, right? No, I should put
It is coming.
like this. Okay. Yes. Okay.
Not yet for me. Ah, yes. No.
It was just a black screen.
Just a black screen. It was the same for me with Alasdair. Black again. Okay, I should do it again. Is it working?
Not yet.
It
Let's
is coming,
see.
Francois. Maybe we should wait a little bit.
No.
No.
You should try to share the entire screen, not just a window.
Yes, I know, but I don't know why it's not working. No?
Not yet.
It seems it is coming,
Coming
but
after it stop.
yes. Francois, would you like to send your presentation to me and then I will share my screen for you? And meanwhile, because probably it will take some time to send the file, maybe Michaela can start her presentation. Is that
Okay.
okay with both of you?
You mean Răzvan?
I'm sorry. Yes, yes, Rizwan. I'm sorry.
Yes. I think Răzvan, can you hear us?
Yes, I can hear you. Do you hear me?
Yes. Are you ready to present your lecture?
Yeah, I
Okay.
can do it. Yeah.
Then we can change a little bit. We can switch the lectures and we will come back to Francois.
Okay. While I'm working with Francois on this, Michaela, can you please introduce Rizvan to the group before he starts his presentation?
Yes, of course.
Thank you.
I will give the floor to my colleague Răzvan Popescu, who is very much involved in mountain research. His main interest is in studying low altitude permafrost, as I told you, as an key climate variable to understand climate change. I will let him to speak more about his studies since he's the best, at least in our country, is a very well-known researcher for this topic. Răzvan, you have the floor.
Thank you, Mihaela. I guess you already see my screen, right?
Yes, we can see it.
Okay. So my presentation is a bit larger than what I studied at PhD and afterwards, which is mountain permafrost. Is about mountain systems. So I will have around a third of my presentation as an introduction about mountain systems in general. And then I will have this special focus on permafrost as an essential climate variable. So why are mountains important and why they matter? They have a threefold importance from a research and from the society point of view. They have an ecological and major climate importance because they support the global sustainability because they provide essential services that support nearly half of the human population. Also, they help with carbon sequestration. They act as biological lungs because they regulate atmospheric circulation and absorb significant amounts of carbon dioxide, as you already seen a bit earlier with the weathering rocks that absorb the carbon dioxide. But also through the forest. They hold a huge chunk of global forest. They also are a biodiversity hotspots. They host around half of the world's plant, even though they hold only a quarter of the Earth's land. So what we should keep in mind is this services for half of the population and half of the human species, while they only hold a quarter of the Earth's land. They also have a geological and geomorphological role because they act as geoscientific laboratories, because we can study processes such as tectonic processes, crustal shaping, orogeny, and subduction. We can study this by measuring how mountains are lifting or how erosion takes place, and what's the annual erosion rates at in geologic times. They also are erosion engines. The geomorphological processes are accelerated in the mountains. So we can, it offers us a nice view on this and a nice opportunity to study such processes. Also, they are climate indicators. Mountains in general are sensitive environments, so they act as climate change sensors. If the climate changes, we see fast its impact on the land and geomorphological processes in this area. But in mountain environments, we can also use different kind of structures, like from the cryospheric sphere, like for example glaciers and other type of ice, and also other geomorphological structures such as lake sediments and other peat bogs and other structures that can be used to study past climate variability. We call these climate proxies. In mountain areas are many of them. Also trees can be studied for such a purpose, and the good thing with mountains is that they are above all least altered, modified by human intervention because of the poor accessibility there. But what is a mountain? A mountain is defined either on elevation or on altitudinal variability. We should, by definition, have an altitudinal variability more than 200 meters per square kilometers, and steep slopes defined as above 10 degrees, and absolute elevation above 600 meters. Whatever land area that fits into these criteria are considered mountains. But also we have other definition by United Nations Environmental Program that classified mountain into 6 classes. And we can see that mountains can be as low as 300 meters, but we should have additional criteria like slope and local relief, land amplitude more than 300 meters, and 5 degrees threshold or 2 degrees Celsius, 2 degrees slope for this class 5 and class 4 respectively. So mountains cover about 36 million square kilometers, accounting for about a quarter of the Earth's total land area, as I told you earlier. Mountains are very dynamic. They have high energetic geomorphological processes because of steep gradients, and also have vertical zonation. They have different climates as you go up. The temperature drops as you go in altitude. They also have a hydrological and climatic role because they are water towers. They provide lots of fresh water for the human consumption. And also they are climatic mosaics. There are lots of different climates in short horizontal distances because of uneven distribution of solar radiation mainly, and because of the slope aspect, and because of the rain shadow effects. We have a large variability in humidity in the same mountain area in relation to the precipitation source. Also, when discussing about mountains, the title of the presentation is called Mountain Systems. What are mountain systems? From large scale to local scale, one should differentiate between orogenic belts, which are intercontinental, as for example, Alpine Himalayan belt. Mountain systems are a part of the orogenic belts, is a distinct part of orogenic belts, like for example Carpathians. Then we have a mountain range, which is a ridge of several tens to hundreds of kilometers that have several peaks and have a unitary geological background and tectonic background, like for example Stara Planina here in Bulgaria. And we have a mountain massif, which is a massive part of the land that stays above the ground and is largely unfragmented by valleys, by deep valleys or geologic faults. So mountain massif, mountain range, mountain system, and orogenic belts. Then I posted some slides about mountain geomorphological hazards, because I told you earlier about their sensitivity in the context of climate change. And we have this classification of landslides that was established in the 70s and then was updated later on in a few more than 11 years ago by Hunger at collaborators. The classification of landslides that will be discussed a bit later. So the mountain geomorphological hazards are mass movements, glacial hazards, periglacial hazards, and snow hazards. And I will discuss each of them in the following slides on short. So the classification of landslides are slides, faults, flows, and complex landslides. Landslides and mass movements are a bit synonyms, and slides is only a type of landslide. So we have here an example of an old landslide from Romanian Carpathians that was probably produced. We don't have the date yet, but we can see nicely the scarp that is now forested, and we can see how this huge landslide, earthquake-induced landslide, changed the flow of the river. Here we have a fall, and mainly the falls processes include rock falls, ice falls, and but mostly rock falls are the main process from this category in the mountain areas. They are affecting the infrastructure and threatening the human life. We have then the flows that includes water, but not only. When we have water, high amounts of precipitation in a mixture with debris, we get debris flows that can, like we can see, not here. Here is a rock avalanche, but debris flow is a very common process. And then we have a rock avalanche. Rock avalanche, even though it seems more like a fall, it's rather a flow, because we have this fluidization of the material that can go much more than normally expected from them. So these are the flows, and then we have the complex landslide, and one of the most common is the deep-seated gravitational slope deformation that are deep landslides occurring on entire mountain slope, like we can see here in Southern Alps in Italy. That creates double ridges, mountain splitting, mega scarps, and trenches. These are most probably created at the transition between the Pleistocene and Holocene, and are found all over the place, and can be easily recognized. And they appeared. They are slow landslides, slow movement, but they have a role in accentuating the instability of slope. So they are a preparatory process for the other types of landslide coming afterwards. Then we have glacial hazards. We are moving now into the cryosphere, which is the frozen layer of the Earth. Glacial hazards, the most important and the most dangerous are glacial lake outburst floods. So when the mountain glacier retreat, they leave behind large moraine systems. And these frontal moraines, as we see here in this scheme, these frontal moraines are usually they are underlain by ice and permafrost, mountain permafrost, and the problem with them is that behind of them proglacial lake appears, and their resistance is not that high. So when you have rockfall producing in and falling into this lake, it creates a wave. It could be a powerful tsunami-like wave that goes above the moraine dams, and it can destroy the dam, and then you can have a huge flood down valley that can destroy, like as we can see here, a hydropower dam in um, on the river downstream. So glacial lake outburst floods are of a major concern in the as a glacial hazards. And other type is ice avalanche. Ice avalanche mainly coming from hanging glaciers, even though they are not so many alarming studies showing that the hanging glaciers are producing a significant more amount of ice avalanches in the last period. We still might expect an increase in this type of processes in the future. Then we have the periglacial hazards. Just a quick overview. I will come back later on some things. Now on this slide, I treat permafrost on global scale. So not only mountain permafrost, you can see here. And the main problem, the main hazards of periglacial origin are related to permafrost degradation. Permafrost, which is a land that is frozen continuously, and with the climate warming, we have either the permafrost degradation, which is permafrost thawing partially or totally, leading to thermokarst landform formations. The land creates the water body. Thermokarst lake, we can see here, which is the land subsides and that forming depression is filled with water. Then we have here a massive thaw slump. Now with the permafrost degradation, a landslide occur because the resistance of the slope decreases a lot. Then we have gully thermokarst because of the permafrost thawing, the soil resistance decrease. So you can have, and with liquid precipitation increasing, you have a more possibility of such processes to occur, like thermokarst gullies. And then we have this type of landslides, active layer detachment slides. With increasing the active layer, which is the part that thaws during the warm season of the permafrost, and if you have a slope, a certain slopes, we can register such phenomena as they are documented here. So this is thermokarst related landforms. Then we have these huge holes that appeared and they were reported after 2010 in Siberia, in Siberian permafrost, gas emitting craters formation because of the gas with the permafrost thawing, the gas inside the permafrost, because the latitudinal permafrost has a lot of organic matter that decays and forms gas, and this gas accumulates below the ground, and at a certain point and it explodes, and it creates, because of the high pressure that is being created underneath, and then you have this type of huge crater like a meteorite hitting the ground. Then we have in mountain areas with the permafrost degradation, we have overall acceleration of sediment transfers by rock slides, as we can see here, by debris flow. The moraines and other type of deposits become loose and less resistant to rain, to gully erosion, and we can see here a debris flow in a moraine. And then we have this rock glacier acceleration. I will come back later on that. But we can see here such a debris lobe from 75, 93, and 2001, how several crevasse-like landform appear on its surface as a sign of accelerating dynamics, movement downslope with climate warming. Then we have snow hazards. We have snow avalanche changes. Snow avalanches happens all the time, even in cold areas, but now they are changing in some ways. We can see here the types of avalanches, but they will increase in frequency earlier during the winter because of heat waves during the winter hitting the mountain areas mainly, and also changes in the snow cornice behavior. Usually the snow cornice fall during springtime, and they cause lots of violent sometimes snow avalanches, but with climate change such events begin to happen during the entire winter, making the mountain environment more dangerous. Then we come to the permafrost part of my presentation. And what is permafrost? Permafrost comes from perennially frozen ground, which is ground defined as not only as soil, but also as rock or debris or any kind of material excluding ice. Ice is not permafrost. That has a temperature below 0 degrees Celsius for at least 2 consecutive years. Okay, so this permafrost has this internal structure that is shown here. We have an active layer at the surface, which is the layer, the ground layer that thaws during the summer because of the sunlight. And then we have the perennially frozen layer, the permafrost itself, that has ice, but is not mandatory to have ice. You can have dry permafrost. And then underneath you have non-frozen ground. This is a thermal profile in depth, and you can see that the temperature, the mean annular temperature is this curve here. That this is the 0 degrees Celsius, and this is the maximum temperature and the minimum temperature during the winter. This is a typical permafrost depth temperature profile. Why do we have this permafrost base? Is because of the geothermal heat of the earth. Okay, with the climate change, this permafrost, this active layer starts to increase in depth, and the problems that I showed you earlier, some of them are starting to occur because of this phenomenon. Okay, so there are several types of permafrost, and I put here the classification according to the spatial distribution of permafrost in an area. We have a continuous permafrost that has a percentage of 90% of an area. So mostly, most land area is covered by permafrost. This here permafrost is thick. It can be as thick as 1,500 meters in northern Asia, in Siberia, or a few hundred meters in Canada, North Canada. And also it can occur underneath the ocean. Yeah, this is the submarine permafrost. With the degradation, we have increased coastal erosion in this area. Then we have this continuous permafrost, which is more fragmented. It occurs on 50 to 90% from the total area, from a total area, land area. Here we have infrastructure objectives occurring that are being affected because with thawing permafrost and the permafrost degradation here, the lands subsides, or we have mainly the creation of those kind of depressions, formation of thermokarst lakes, and so on. And then we have sporadic permafrost. Sporadic permafrost is where only 10 to 50% is underlain by permafrost. The active layer is thicker, as you can see here. This is in the forest area. I forgot to tell you that continuous permafrost occur where mean annual air temperature is below -8. This continuous permafrost is variable, but mainly below -2, -3, and sporadic permafrost mainly with negative mean annual air temperature. Outside of this, we also have patchy permafrost, isolated patchy permafrost, which is below 10%, and extrazonal permafrost, which is low altitude permafrost in temperature, mean annual temperature, well above well above 0 degrees Celsius. That I will talk a bit later. So continuous, discontinuous, sporadic, isolated patchy, and extrazonal low altitude permafrost. Now I'll talk specifically on mountain permafrost, because I also forgot to tell you that from the distribution we have these types of permafrost, but from the point of view of where it occurs, we have latitudinal permafrost, which is at high latitudes, and also altitudinal permafrost at high altitudes, which is mountain permafrost. And my presentation is focused on mountain permafrost that can occur in these types of structures on rock walls, which is exposed bedrock in mountain areas, steep, frozen bedrock, frozen rock walls, in talus slopes. These are talus slopes are formed by accumulation by rockfalls or rock slides from the rock walls at the base of these walls, and there is a steep landform formed from the conjunction of several debris cones. Then we have in bedrock areas covered by debris, but a thin layer of debris, called fractured bedrock, and the most common type and well easier to be recognizable, rogue glacier permafrost, that I will discuss and I will detail later. But in general, about mountain permafrost, we can say that includes 30% of global permafrost. The rest is latitudinal permafrost. It has a large spatial variability on short distances because the uneven distribution of solar radiation, the northern slopes obviously are much more favorable to permafrost development. Typical environments are the one that I already mentioned here. Okay, I told you about rock glaciers. Rock glaciers are lobate or tongue-shaped landforms occurring in mountain areas. These huge debris landforms, debris accumulations, they can be coarse debris accumulation, or they can be made out of fine materials. And they have some characteristics like specific morphology of ridges and furrows, as you can see here. These lava flow like features, which is indicative of slow movement downslope, and by slow I mean from a few centimeters to a few meters or tens of meters per year. So they are less active than real total cold glaciers, which is the result of the creep processes, permafrost creep processes. They are important landforms. They are diagnostic landforms of the presence of permafrost in a mountain environment. These are two such landforms in Retezat mountains from Romanian Carpathians. The formation of rock glaciers includes the debris cone phase, that creates a cold microclimate. These are cold air traps. So after the formation of or during the formation of the debris cone, you have the permafrost initiation. Afterwards, it starts to flow downslope, and then you have the full rock glacier development. Here we have one of the most studied rock glaciers from the world, from the Swiss Alps, Myrtle rock glaciers, where we can see this typical morphology of ridges, arcuate ridges, and furrows beneath. The terminal part of such a tongue-shaped rock glaciers is represented by a steep front, as we can see here, and the formation by measuring how fast the rock glacier move, we can find out how old is the landforms. But usually, rock glaciers found now are post last glacial maximum, if they are relict or inactive, that I will tell you a bit later. But the active ones are recent, are Holocene in age usually. By permafrost creep, I just wanted to show you how permafrost creep occur or develop. This is a view section of rock glacier, where we can see the debris layer, the coarse debris layer at the top, and then the permafrost creep, which is debris and ice. The permafrost, in order to creep, should be super saturated in ice, which is the volume of ice should be larger than the volume of air inside the debris. And this permafrost creep happens, most of it, in what is called the shear zone, which is a layer where you have humidity, you have clay, so fine materials that allows the creep to produce. And here we have some profiles of movement in the same rock glacier that I showed you earlier, Murterl rock glacier, where they measured the rock glacier movement in depth using some instruments called inclinometers. And we can see that below this shear zone, we have mostly no movement, while in this shear zone, most of the movement happened. But also, the permafrost deformation happens above this shear zone, and we have the cumulative movement higher at the surface. We could summarize, or we can characterize the permafrost creep as a passive movement. Usually here we can see there is some movement, but in some rock glaciers, in many rock glaciers, the top layer move passively. The most of the movement happens in this shear zone. There are several types of rock glaciers. We have active rock glaciers. They are moving in the present. We have inactive rock glaciers. They have permafrost, but they don't move anymore. And we have relict or fossil rock glaciers. They have the typical morphology of ridges and furrows, but they have no permafrost and no movement. However, it was shown that recently by using a new technology called interferometric synthetic aperture radar, or INSAR in short, that the movement is very complex, and also in what we usually would call relict rock glacier, we can have some movement, as we can see here in a rock glacier from Romanian Carpathians. There is some movement of below 3 centimeters per year, or even below 1 centimeter per year. And also in this rock glacier now, we have a new an updated classification of rock glacier. We have active rock glaciers. They are considered those that are moving more than 10 centimeters per year. Transitional rock glaciers between 3 and 10 centimeters, and relict below 3 centimeters. So this new classification also involves movement in relict rock glaciers. But this is a classification that only takes into account movement and not permafrost presence, because, as I will show you on these slides, it was recently shown, and we also contributed in this matter. In Romanian Carpathians, there are some rock glaciers that have the typical signs of relict, like for example here, the vegetation is the main proxy for rock glacier inactivity or relict status. When you have vegetation, shrubs, or even trees, it's a clear sign of relict state of a rock glacier. But it was shown that permafrost can still occur in small pockets in such landfalls, as you can see here in Italian Alps at 2,300 meters, or even in this rock glacier here, that is also have trees on its surface. So you can understand now why rock glaciers are called climatic indicators, because when they are relict, they indicate past colder conditions. When they are active, they indicate a cold, stable climate. Okay. Permafrost, so, is an essential climate variable. This concept of essential climate variables was established by an international body, international institution of Global Climate Observing System, GCOS.
Razvan,
Yes, yes.
I'm sorry to interrupt, but you have to speed up, okay?
Yes, yes. Okay.
Okay, because we should finish, based on our agenda, we should finish at 8, and we have one more presentation, okay?
Okay. I thought I have 40 minutes and I have 10 minutes left.
Speed up if you can,
Okay,
please.
okay.
Thank you
I
so
will
much.
speed up. So we have this global climate observing system that established 55 essential climate variables. Permafrost is one of them because it filters out short-term meteorological noise and it shows the trend in climate change. We have three variables, three parameters of permafrost as an essential climate variable, which is temperature, active layer thickness, and rock glacier kinematics, which was added a few years ago. So the velocity of rock glacier is an indicator of climate change. Permafrost temperature is measured in boreholes, drilled boreholes across the globe. They are monitored by or inventoried by what is International Global Terrestrial Network for Permafrost, and we can see in these graphs that the permafrost is warming around the globe. Another parameter is the active layer depth, and we can see here that active layer in mountain permafrost is expected to increase by 2050 and by 2100, and we can see that with permafrost degradation, the rock glaciers, the active rock glaciers, started to increase their activity. They increased activity in this case from a few centimeters per year in the 80s or 90s to more than 5 meters per year. They are called destabilized rock glaciers. How do we study permafrost in a mountain environment? We detect, we map, we model their spatial distribution, we determine its physical characteristics, and then we monitor them long term. How do we detect? We search for their specific morphology of ridges and furrow. Then we assess by geomorphological indicator and vegetation indicator into relict, inactive, probably active. Then we make thermal measurements, like for example, bottom temperature of late winter snow cover. And we map the temperatures below -2 or -3, which are indicative of permafrost presence. Then we use miniature data loggers, which register continuously throughout the year from a few minutes to a few hours interval, and they show us the heat exchanges between ground and atmosphere. We measure spring water temperature of the springs outflowing from the rock glacier, and if the temperature is below 2 degrees, we have permafrost probable in that rock glacier. We can also use, and I used this method I used this method in this project, TRACE, in what is called low altitude permafrost site. We have a site in Romania, the Tunata talus slope, which is a basaltic talus slope that has is very low in altitude at 1000 meters, where the mean annual temperature is +7, and it still preserves some permafrost because of the so-called chimney circulation. We published a paper on that, and we could detect in this project using a thermal infrared drone the warmer evacuation areas of such talus slopes, and we detected such phenomena also in other talus slopes in Romania. As you can see here, these red areas are the warmer evacuation areas. Here you can see how air circulates during the summer. The cold air outflows from the talus during the summer. And okay, here also we can see the cold, very cold area on the bottom of the talus and the warm area up. The same methods we applied on thermal infrared scanning on rock glacier from Retezat, and we can see some cold and some warm, but we didn't detect specifically the chimney effect that that is found in low altitude permafrost sites. Then we have the geophysical methods, other indirect methods for detecting and mapping permafrost. This is the heavy equipment that is used to put some electrical current in the ground, and then to measure the resistivity of the ground to the passing of electrical current. And you can have these tomograms, and the ice is very high, has high resistivity, and can be detected by this method. You can see here how it looks like in the ground. We use some steel electrodes put in the ground, connected with this cable to a computer and to a battery. Then we have this seismic refraction method that uses the P wave velocity produced by a hammer, and by measuring their travel speed with depth, and using these types of geophones. These are called geophones that are put into the ground. You have to use this hammer in order to create a seismic wave, which is connected to a computer, in this case to a phone app. Then a direct method for permafrost investigation include borehole drilling and coring, and you can see here we started this the last year actually, to use a portable drilling equipment in order to make such a drill in a rock glacier. And after the borehole is being drilled, we put sensors with cables in order to measure the temperature inside and to see how it changes multi-annually. Here is from the detonata side where you use a heavy equipment by coring, which means to retrieve a core while drilling, not just making a hole, allows to create this stratigraphy of internal stratigraphy of a landform and to understand better its evolution and dynamics. Then we measure rock glacier kinematics using a total station. In this project, we were able to install some fixed metal platforms in the ground, and we used a robotic total station that increases the accuracy because, as you seen earlier, the rock glaciers in Romanian Carpathians are moving very slow, sometimes even below 1 centimeters, and we achieved high accuracy of half of centimeters accuracy. The robotic total station means that we don't have to touch the total station. It moves alone by itself, and it finds the target that is also installed in the rock glacier in several points of measurement. Then we have these maps where we can detect when it moves and how much it moves, because we measure this several years, once a year. This is a short video of rock glacier front in Retezat Mountains. This is how it looks like. Its course is this typical morphology. And with this, I came to my final slide, and I thank you for your participation. And if you have questions, please, you are welcome.
Thank you very much, Razvan, for this interesting presentation. Just to inform the audience, Razvan Andrei Popescu is a lecturer and researcher at the University of Bucharest, Faculty of Geography, in the Department of Geomorphology, Pedology and Geomatics. He specialized in mountain geomorphology, examining the impacts of climate change on mountain landforms and conducting glacial and periglacial reconstruction using geomorphic proxies. So it was very important that we have a lecture from Razvan about this subject. Because the climate change affects a lot the mountainous areas, as you have understood. His research primarily focuses on mountain permafrost in the Carpathian region, the phenomenon of low altitude permafrost, paleoclimate reconstructions, and current morphoclimatic changes in mountain areas. He serves on the board of the Romanian Association of Geomorphology and is a member of the European Geoscience Union and the Permafrost Young Researchers Network. Also, Razvan is a member in the Romanian team of Trace project, so we had the opportunity and the privilege, I could say, to work with him. Thank you very much, Razvan. We don't have time for questions, but just to let students know that they can always come back with questions and comments, and all the lecturers are happy to come back to you.
Thank you also.
I see that there is a comment here. Okay, I will read that. In addition to the presentation about permafrost, there is a documentary about Arctic permafrost made by Greek journalist Avgeropoulos. This is written by a student of ours. The documentary is in English with subtitles, and you can watch it at cinemas in Greece and Cyprus. Most probably it will be also online for free in the future, probably on Earthflix in the documentary section. Thank you very much, Vasilis, for this comment. I didn't know that, and I was saying to somebody today that I always learn something, even from my colleagues and my students. And so thank you so much. I will
I
keep it.
learned the word permafrost today for the first time from my colleague, that she saw the documentary and told me about it. And today we had this presentation about permafrost. So it's a huge coincidence. That's why
Yeah,
I started it for. I didn't have the chance to watch it because in Thessaloniki it doesn't play anymore, but you can watch it in Athens or online.
perfect. Good. Very nice. Thank you so much.
You're welcome.
Now we will go back to Francois. I will not introduce him, I have already done it. So I will just share for him mm, uh,
Yes, I
the
think we can.
presentation. And you will have to let me know when you
Of
wish
course,
to,
yes. Thanks
go
to
to
you,
the
Nikki,
next
and
slide.
sorry to the students. Sorry for this. I don't know what it is working, what it is not working. But anyway, we are a team, so we will manage to give the lectures. Well, so I should be short and keep your attention. So it's quite challenging for me. Well, my talk deal with coastal dynamics and deltaic systems. So you can go on the second. Next, please. Okay, it is on the coastal zone, and you know that the coastal zone is very used for human activity. So I don't give a long introduction about that. Sometimes you are going to on the beach, and of course there is also urbanized activities. So next, please. Well, today I'm speaking about two different environments on the coastal landscape. The one is related to deltaic system with large beaches with where the waves can propagate and the currents are more or less free. And on the other part, my talk is on more closed system. We call it pocket beaches on the right. This is a pictures of a pocket beach in Corsica. And in these kind of systems, you can consider that the sediments are they stay between the two headlands. So I will give the talk on this coastal feature because this is the coastal landscape that we investigate in this program. So next, please. So the first is connecting to the deltaic system. And probably you know that there is a classical way to classify the delta, because the delta is a kind of opposition between the river input and the marine forces. It could be current, it could be tide, it could be waves. There is three kind of delta, and we are speaking today about the wave-dominated delta. That means that the wave is the main process which organizes the shoreline position. So next. And next. And we are going to speak about the Rhône Delta. Rhône Delta is in France, in the south, close to Marseille, less than 100 kilometers. And here it is. You see that you may see the well, I cannot I cannot use the mouse, so I should describe. There is the large arm. There's two arms. The big one, you see it probably on the screen. And it is a coastline very reshaped by the waves, a sandy coastline. We'll discuss, yes, this is the hook and this is the mouth. And if you are moving on the west part, you'll see that, yes, you can go there. It is, okay, again, and again, there is several speeds. Yes, next, please. So the Rhône Delta is a Holocene construction. This is not my topic today because some colleagues are speaking about that better than I. But you should keep in mind that in the deltaic systems, the sea level position, the sea level elevation play key roles, but river sediment inputs are also very important. Of course, the waves after are reshaping the process, the coastline, sorry. Next, please. So what we did is we have a look on the long-term shoreline change, and you have on the bottom an image of the shoreline changes along the coastline. And for example, you may see that the shoreline advance more than 1 kilometers. Yes, on this part, this is a spit, and there is not a lot of spits. There is 3. On the opposite, on the west part of the delta, there is another spit, and the advance is at least 2 kilometers during the 20th century. But a large part of the coastline is under erosional regime, and these parts nowadays are used, receive, some equipment, some dikes, groins, and so on. So we will discuss about that on the next slide, please. Yes, so the thing is that probably, as you know, when you are looking on the shoreline evolution, on the shoreline change, you can use this indicator to define what we're calling littoral drift cell. That means that an erosional area feed an accretional area. And when you have these 2 parts, you have a cell. If you are looking on the cell 4, for example, on the west part of the Rhone Delta, you see that there is accumulation, and also there is erosion. So there is a connection between these 2 areas. It's very common to use this concept nowadays for management and engineering practice. So it's a good way to organize how the shoreline is moving and to think in terms of a sediment budget. It is the first step. So we organize the Rhone Delta like this, and most of the coast can be organized with littoral cells. So next, please. So now few slides on the shoreline change on a typical case. You see that the shoreline is a retreat on the pictures, and on the right, if you have a look of the figure, no, sorry, come back, please.
Sorry.
Yes, you see that the graphs indicate the average retreat in this area, and you see that after the groins and dike, the shoreline more or less stabilized, because before the shoreline retreat was around 8 meters per day, not per day, sorry, per year, and the shoreline stabilized. But nowadays the shoreline is around 6 meters because the groins and dikes collapse. So as they collapse, the shoreline retreat starts again, and you see on the pictures that there is a kind of retreat where the dikes collapse, and there is a deposition close to the on the east part of this retreat. So we can have a look on the other slide, please. The groins and the dikes sometimes are collapsing, but sometimes they stay on the same place because there is a lot in this area. And you see that in this area, it is possible to stabilize the shoreline. But of course, there is a trouble when you stabilize the shoreline because there is an erosion under the water, and this erosion is going on. So the future of this urbanized area is very connected to the groin and the dikes. And thinking about the previous slide, you can imagine and believe that you only stabilize the shoreline if the groins stay on the same location and if the groins do not collapse. So it's challenging for the futures, because you have to pay again and again to fix the shoreline position. So next, please. Another evolution, which is more natural in this part of the Rhone Delta, you see this is a spit. Have a look on the right, on the left on the map, and you see that there is a retreat and there is a kind of elongation of the spit. It is close to the ground move, and there is a few reverse sediment input. So if we have a look, yes, here, you see that this is a shoreline retreat, and at the beginning of the observation, the retreat was very, very fast, around 10 or 20 meters per year, and the retreat decreased, and nowadays, the retreat is around 2 meters per year. And this is a natural process. This is what we are calling a kind of regulation of the retreat, because the morphology of the coastline first was a little bit curved, and now it is straight, so the currents are not so intense, and the shoreline retreat reduce. So just to show you that sometimes by natural process, the shoreline and the erosion reduce just because of the adaptation of the morphology to the waves and to the marine forces. Yes, exactly there. So next, please. And what we can do is to calculate, it's very simple to do, the impact of the sea level rise on the shoreline position. You take the slope of the beach face. Well, there is a debate with a colleague to select the good slope to use, but in that case, if you increase the sea level, you can estimate the retreat related to the increase of the sea level. So if you have a look of the retreat during the natural period, I mean without structures, the average retreat on the original areas is around 300 meters, but if you only use the silver rise, the retreat is 7 meters during the same period. So that means that in that case, the shoreline position is not very controlled by the sea level, but is very controlled by the wave actions. Of course, it's a very simple methodology, but it's very useful to give a kind of order of magnitude. And we will see for the pocket beach that the evolution is different. So next, please. Well, so, okay, there is a retreat, but in the same times, during storms, you know, the waves are coming on the beach and destroy the dune, and they put the sand behind in the lagoon. And this process is what we are calling overwash. There is deposit of sediment in the lagoon. And this process occurs during big storms. And the thing is that there is a slow sea level rise, but in the same times, there is sediment input. There is sediment movement on the back, and sediment pushed into the lagoon. So you can compensate the elevation of the sea level by this sediment accumulation. So the challenge for the future is to organize, to permit this process, because this is a natural process to compensate sea level increase. So we can go on the next slide, please. And well, you see that if you are waiting enough, when this dike was built, the beach was around 50 meters. And now the dikes collapse and the beach is recovering behind the dike. So if the dike collapse, the dunes, and not exactly the dune, but the beach can recover. So it is a positive signal for the future, this kind of natural process. So next, please. Well, we now I should give some few input on reverse sediment input, because we are in a deltaic system. And in that case, as in a lot of deltaic systems, there is a decrease of river flow and decrease of reverse sediment input. So this is one of the reasons to explain the erosion. So next, please. Well, it was for a wave-dominated delta. Now, few words on pocket beaches. Pocket beaches, you know, there is several types of pocket beaches. Some of them are very close system. It is on the right figure, and we are speaking about this kind of pocket beaches. It's a very common feature along Mediterranean coastline, and there is a lot. Next, please. Some pictures, and we select for the studies, we select several pocket beaches, natural, with not human intervention. And these kind of pocket beaches, you know, are scarped. On the behind there is a scarp, so it's not possible for these pocket beaches to retreat. And we did some measurement with students, and during this very nice and enthusiastic Erasmus Plus program, and you see that it can be you on the slide. So the next, please. Well, so what we do is we compare shoreline position and bathymetric evolution in this kind of environment. Next one, please. So the result is that all the pocket beaches observed are under retreat. And the retreat is around, well, 10 or 12 meters during the 20th century, which is a very, very slow, because it is 12 meters in 1 century. Remember when I was speaking about the Rhone Delta, it is 12 meters per year, not everywhere, but in some places. And so as the beach cannot retreat, of course, they are slowly disappearing. Half of the beach area has disappeared. So next, please. If we compare bathymetry, you can observe this kind of result. Erosion is in red, and accumulation is in blue. It is a comparison in long term, secular comparison with bathymetry. And this erosion is going down, the sediments are going down to the profile, and they are in around 4, 5, or 6 meter depth. There is a kind of translation of sediments from the upper part, from the shoreline, to the offshore. And because of this environment, there is not overwash processes. The sediments are not very often, they have not opportunity to move onshore during overwash processes. The sediment budget is reducing through time. So next, please. So we use the same methodology to simulate the sea level increase, and we observe that in the past, during the last century, the sea level rise can explain the retreat, and for around 50%, which is very, very important. And in that kind of environment, the sea level has a very strong impact on the shoreline position. Well, it's not surprising, because the waves, you know, it is a protected area, so the waves are very slow. So the retreat is very connected to the sea level position, and the future connected to the sea level rise. So next, please. Please stay, because this is almost the end. So if we do that for the future by using the projection of the sea level on several beaches, you can see that most of them will disappear in the future. So this is because they are scarped, because they cannot easily retreat. And if we think about that, it is something, as said our colleague Alice there during the first talk, is very well and very important to know how to simulate the future in order to organize the society, the coastal management, to protect against that. I mean that he speaks about climate anxiety, so you should know the process. Like this, you know how to organize and to not to receive the information and say, okay, this is the end. And because of course there is opportunities to protect this kind of area. We will talk about that later. Next slide, please. I mean later, which is not in this talk, in the simulation talk. If you use this concept, can you click again, because there is a little change? Yes, this is my only animation. If you use this concept, you see that this beach is going to disappear. So you should imagine some engineering and natural basis solution to protect this kind of area. The next, again, 2 slides. As a resume, you can say that even if the sea level is rising, some beaches can adapt. And for example, on deltaic systems, they can adapt. If we let the beach and the dunes moving onshore, this is only condition. And this is the last slide, the next one. Yes. So the last slide is, even if sea level rise and the shoreline retreats, what matters most is the shoreline's capacity to migrate landwards and to reform first. So there is opportunity to let the shoreline move. It is the end.
Thank you very much, Francois, for this talk. This is, in fact, the end of today's workshop. Just to remind you that 3 more are coming for the Greek community, but people from abroad, you are also always very welcome. Just to remind you that to fill in the form that my colleague Evangelos has sent in the chat, please do so in order to send to you the certificates, and also to remind you that next week we have another workshop with another subject, maybe, I don't remember right now, but maybe Michaela can remind us. It's about Holocene changes of landscape. So we will go back to paleoenvironmental and paleogeographical changes with different colleagues from our group. So you are all welcome to join. There is something else that we will discuss, always related to climate change, because from the past we can understand what has happened, and then we can be better prepared and better understand what is happening nowadays, and better prepared for what is coming. So I wish you a nice evening. Thank you for joining us. See you in 1 week. Don't forget to fill in the forms.
Thank you so much.
Thank you.
Thank you.
Thank you.
Thank you. Bye.
Thank
Bye.
you. See you next week.
Bye.
Bye-bye.
Bye.
Nikki, thank you for your help. I'm very sorry and very confused.
Don't worry, it happens. It is the Murphy's Law.
Okay.
everything happens the moment that it shouldn't happen.
Okay. Okay.
Okay. It was nice. We had more than 100
Yes, yes,
participants. That was
yes,
great. They stayed until the end. That is really
yes,
great
yes,
because
yes,
we
you're
are
right.
half an hour late.
Mm, But
So,
I realized that Greek people speak a lot, and Greek students speak English. So I am a little bit worried about the French students because I start to make the announcement and well, we will see. It is in 2 months, so I have time to.
everything will go fine. I'm sure about that.
Okay.
Okay. Good
Okay.
night.
Good night.
See you. Bye bye.
Thanks.
See you in Greece in few days.